Good morning. Myself, Dr. Shaila Dinkar Apte. Today, we'll continue with the FIR filter design. Last time, we have gone through the Fourier series expansion method for FIR filter design using rectangular window. Now, we consider different windowing methods. Digital signal processing by Wiley publication. This is a book published by me. You will get all different contents that I am talking in the lecture. You can get it from this book. We will just recapture whatever we have discussed in FIR filter design. That is the design of the brick wall filter. We discussed the brick wall filter and we said that let us replicate this brick wall filter on either side of pi and minus pi. So we'll have the replicated response around 3 pi minus 3 pi and so on. And then we said that let us take the inverse transform, that will be a discrete time impulse response of the filter, because we are taking the Fourier series for the periodic signal in the frequency domain. So here if we just interchange the time and frequency, we will get the same thing. But this Fourier series expansion, this particular name is little confusing, as I said. We are writing the Fourier series for a periodic signal in frequency domain. And this time domain response being a sinc function, it is varying between minus infinity to infinity. This is because the frequency domain response has a sudden change at the cutoff frequency. At the cutoff frequency, the response becomes suddenly equal to 0. That is why we call it as the brick wall filter. Now, can we design this FIR filter? The answer is no. Because we want to have finite impulse response coefficients. And when we want to have finite impulse response coefficients, we cannot deal with the infinite frequency infinite filter coefficients. Those are obtained using the infinite sinc function. So there is a need to truncate this impulse response between some minus q to plus q, and we'll have to select this minus q and plus q in such a fashion that the energy of the coefficients above q and energy of the coefficients below minus q is very, very small and can be negligible. And then this particular truncation can be justifiable. When we say I am truncating it, it is as if saying that I am passing it via a rectangular window. And when I pass it via a rectangular window, there is a sudden truncation in the response. Because of this sudden truncation, Gibbs phenomena occurs. And this is because of this, we get oscillations near the band edge of the filter. Also, there are side lobe amplitude, side lobes are there, and the amplitude of the side lobes is large. And so the stop and attenuation is not as expected, it is low. So the frequencies, after the cutoff frequencies, we can say that they are not fully attenuated as expected. And the cutoff is, but the cutoff is relatively sharp in the sense that the transition width is relatively okay. But the side lobe amplitude is large. There are small oscillations also in the passband. So we need to reduce all these effects. So we want to improve on this design. What can be done to reduce the transition width? We can increase the filter order. But how far to increase the filter order? The filter order in digital domain can easily go to 50, 100. But surely we cannot go above that because the computations will be large. The number of coefficients that we require to calculate will also increase. And that is not practicable. The secondly, we will have to use a smooth window. This is recommended so that we can reduce the side lobe amplitude. Now let us see. This is the infinite impulse response that we obtain for the periodic function in the frequency domain. And what we do is we truncate it between minus q to plus q. That means we multiply it by the rectangular window function between minus q to plus q. This is a discrete time function, of course. When we multiply sample by sample, we get the corresponding window coefficients between minus q to plus q. The coefficients above plus q, coefficients below minus q, we are just making it 0. We are just suddenly truncating it. Because of this sudden truncation, what happens is, if you consider the magnitude plot, here you will find that the cutoff frequency that we considered was 1000. So here the transition width is not very large. I am getting the cutoff at 1200 something like 1200. But the side lobes are large. The side lobe amplitude is around, say, minus 20, 22 dB, which is not sufficiently low. So the frequencies above cutoff, they are not totally eliminated. They are remaining. Of course, the linear phase response is there in the passband. If I increase the filter order, as I said, I can increase the filter order to reduce the transition width. So when I increase the filter order from 21 to 2151, here in this case, you can see that the transition width is reduced. Here the frequency response comes down at 1100, and here it comes down at around 1200 or 1250. So the transition width is reduced in this case if you increase the filter order from 21 to 51. But what happens to the side lobe amplitudes? Side lobe is remaining at the same level, and in fact the side lobe frequency has increased. There are more lobes appearing in the stop band. What is the significance of this particular linear phase? The phase is linear with respect to frequency. Means what? There is a constant group delay, because group delay is dd psi of the corresponding phase. So when we differentiate this linear phase, we will get a constant group delay. What is the significance of this constant group delay? When we apply a signal with different frequencies as input to the filter, all these frequencies will be equally delayed. The corresponding phase delay will be constant for all the frequencies. That means there is no phase distortion introduced in the output of the signal. This is the main advantage of using the FIR filter, which is a linear phase filter. And this is the requirement for the speech signal. So normally for speech signal, we use FIR filter design rather than IR filter design. Because we'll see that in case of IR filter, the phase response, you cannot predict what will be the phase response, because it is not having linear phase. Now in this case, because of the linear phase, no phase distortion is introduced in the output of the signal when it passes via the filter. So that is the main, you can say, advantage of using the FIR filter. Now let us analyze this. So when we consider the frequency response, frequency domain response for the filter, we find that the corresponding Fourier transform of the window function gets convolved with the ideal filter response, because in time domain we are having multiplication of the rectangular window with the corresponding impulse response, that is the sinc function. In the frequency domain, what will happen? The Fourier transform of the window function, that means the frequency response, actual frequency response, ideal frequency response, will get multiplied by the Fourier transform of the window function. And when it gets convolved, you will see that in the main lobe, you will find that there is some, you can say, there are oscillations near the bandage of the filter, and also there are side lobe, side lobe amplitude is large. So all these side lobes and a small ripple in the passband, all these effects, they are called as Gibbs phenomena, or it is called as ringing. And the side lobes, those are appearing, it's called as the frequency leakage. The amplitude of the side lobes is required to be reduced. How you can reduce that? We'll have to use a window function which has lower side lobes. So we'll have to select the window function so that we'll get low side lobe amplitude. So what is the requirement finally? We want to use a window function with a thin main lobe width. That means the transition width will have to be smaller, and we will have to use a window functions which is having smaller value of the side lobes so that the ringing can be reduced. Both these requirements cannot be fulfilled at a time. So I will say that there is nothing like free lunch. If somebody is calling you for lunch, remember that he has something in his mind. So if you want to get smaller main lobe width, the corresponding side lobe amplitude will be higher. And if you are reducing the side lobe amplitude, the transition width will also increase. So let us see how to compromise on this. So let us concentrate on the following windows: Blackman, Hamming, Hanning, Bartlett, and Kaiser window. Let us consider the window function. So these are the equations for the window. This is given for Blackman window, Hamming window, Hanning window, Bartlett window, and this is a Kaiser window. You can see that the function in the Kaiser window is very complicated. This is a Bessel function. I0 is a Bessel function of order 0. So calculation of the Bessel functions is very, very difficult. So you will be getting certain advantages in Kaiser window, but at the cost of higher computational costs. That is why I said that there is nothing like free lunch. And for rectangular window, it is 1 for the passband and it is 0, simply 0 for the stopband. So let us see how these window functions would look like. The dotted line is the Blackman window. Very small dots is the Hamming window. This close to that is the Hanning window. The equation or the plot with the plus sign is a Bartlett window. The plot with the star is a Kaiser window. You can see that this Kaiser window function resembles, this is what it is, and it resembles the Gaussian window, and the corresponding, you can say that the Fourier transform of the Gaussian window is almost same as the Gaussian window. That means the side lobe amplitudes will be very, very small, but the computational cost will be very high. In case of Hamming window and Hanning window also, it is a smooth function. So the side lobe amplitudes will be low, but in that case, the main lobe width will increase. You can see that the main lobe width is large. So let us consider the use of the Hamming window. So this is with the these are the coefficients with rectangular window function. That means we are truncating between minus q to plus q. Now, when we are using Hamming window, we'll have to similarly calculate the corresponding filter coefficients, same as we have done using Fourier series expansion method. Then we'll have to calculate the Hamming window functions given by the equation and then multiply the Hamming window coefficients with the corresponding filter coefficients. Those we have calculated using Fourier series expansion method. So when we multiply, the corresponding impulse response of the filter will get modified because of the window is not a rectangular window. Now it is a smooth window function. So you will find that these corresponding coefficients are reduced in amplitude. These coefficients are also reduced in amplitude. And see what will be the effect on the frequency response. See, here we are considering the filter coefficients. These are the window coefficients, and we multiply it by the window coefficients to get the modified coefficients for the filter. Now, after using the Hamming window, what happens to the frequency response? Here you will find that the transition width is smaller. The corresponding frequency response comes down at about 1200. But here it is coming down at 1700 almost. That means the transition width has increased. But what happens to the side lobes? Here side lobes are about minus 20, 22 dB. Here it has gone up to minus 50 dB. So in the stop band, the response is sufficiently gone down. That means the corresponding attenuation is sufficient so that we can say that the corresponding frequencies in the stop band are attenuated, but the pass band is extended. and you will find that the transition width has increased. If you want to reduce the transition width, as I said, you will have to increase the filter order. So additional cost will be there because of the competitions. So consider the performance of these window functions. We are writing the window name, then transition width that is obtained with this window, then minimum stop band attenuation that we can get. So if you consider the rectangular window, the transition width will be 4 pi by capital M, where capital M is the filter order. So if you increase the filter order, transition width will reduce. Minimum stop band attenuation that you get is only minus 13. So which is not recommended because the stop band is not really a stop band in that case. Consider the Bartlett window, the stop band attenuation is minus 27. For Hanning, it is minus 32, and for Hamming, it is minus 43. So if you consider this transition width of 8 pi by m, and then Hamming window is considered as the best because it is giving a maximum stop band attenuation. But if you want to reduce this further, then you will have to use the Blackman window, but in that case, the transition width increases. So nothing like free lunch. If you want to reduce this, transition width will increase. So in that case, to reduce again the transition width, you will have to increase the filter order. So that is how it is. So we'll have to have a trade-off. We see that the side lobe amplitude is small. If we want to have it small, then the width of the main lobe and hence the transition width increases and vice versa. We cannot achieve both. We cannot say that the side lobe amplitude must be small and also the transition width will have to be very, very small. We cannot achieve these two things at a time. If you are working hard, you will get means better marks. But if you do not work hard, you will get less marks. You cannot achieve both the things at a time. That means low efforts and high marks. Not possible. So for the same transition width of 8 pi by m, the stop band attenuation, we have seen that it is lowest for Hamming window. So normally we prefer the Hamming window. The order of the filter selected will have to be increased as per the transition width specifications. Those are given by the user. Now, if you want to have a trade-off, that means if you want to achieve both at a time, then not just the filter order, but you will have to have one more parameter for adjustment, one more degree of freedom. So that is achieved in this case, Kaiser window. So in this case, order of the filter is decided to achieve the transition width that is specified. And then there is a parameter beta for calculation of Kaiser window coefficients. And this beta is to be designed to meet the requirements of the stop band. So here I can try to achieve both. So I can try to make the side lobe amplitude as small as possible, and I can also try to reduce the transition width by using the filter order. So here I get 2 degrees of freedom, not just the filter order, but I can use parameter beta, which is the second degree of freedom, and then I can get the smaller transition width and smaller stop band attenuation. Larger stop band attenuation. This allows the designer one more degree of freedom for the filter design. But at the cost of what? Higher computational cost because it is using the Bessel functions. Calculation of the Bessel functions is very difficult. So there is some Bessel function chart is also available nowadays. But again, yeah, you will have to have a look up for the Bessel function chart and then evaluate the coefficients. So let's consider one example for the design using Kaiser window. For design using other windows, what you have to do is simply use the equation of the window, calculate the window coefficients, multiply the filter coefficients with the window coefficients, and then you design the filter, right? Designing of the filter means design the filter coefficients. Now here, design FIR filter using Fourier series method to meet the following specifications. These are the specifications given to you. Cutoff frequency is 1600, sampling frequency 8000, minimum stop band attenuation is 40 dB. Transition width specified is 0.3 pi and the stop band edge is 0.5 pi. So the transition width is 0.2 pi. That means the corresponding transition width will vary from 1200 to 2000 hertz. 0.3 pi, or how much it will come to? Pi is 4000. So 0.3 of pi, so 0.3 of 4000, so 1200. That is correct. And this 0.5, so 0.5 into 4000, this is 2000. So 12,000 to 2000 is the transition width given as sufficiently large, and then the attenuation is 40 dB. Let us see how to design. The design is fairly complicated. We will have to consider the cutoff frequency. So cutoff frequency will be in between the passband edge and the stopband edge, that is the center of that. So it is 0.4 pi, that means 1600 hertz. Then you calculate the parameter alpha. Alpha is minus 20 log of delta S to the base 10. Now what is alpha? Alpha, the attenuation is specified as minus 40 dB. So for this minus 40 dB, you calculate what will be delta, that is the attenuation. That is attenuation is delta is 0.01. Now, for this particular alpha that is specified, you calculate the value of beta. Now, this beta is calculated using this equation for different values of alpha. Now, here this alpha is minus 40 dB. So, it comes between this 21 to 40, 50. So, we'll have to use this second equation and calculate the value of beta. It turns out to be 3.3953. So, you'll have to do this calculation and calculate beta. You have alpha, you have beta, you have delta. Now, transition width is 0.2 pi. Now, to get this transition width, I'll have to calculate the value of the filter order using this equation. I know the value of alpha. Then I put the value of transition width in this case, and I'll get the filter order as 22. So what should be the value of Q? The filter order is 2Q plus 1. So I'll have to use the value of Q accordingly. So the value of Q I can use is equal to 12. Okay, so I can consider M as order as roughly 25, just higher than that so that I meet the specifications. And after I calculate this filter order, I know beta, I know the filter order, that is capital M. Then I can use this Bessel function equation and calculate the window coefficients. These are the Kaiser window coefficients. Now multiply these window coefficients by the filter coefficients. Those we have already calculated using Fourier series expansion method. Now in this case the cutoff frequency is 1600. So accordingly Fourier series coefficients will have to be calculated again and then find the filter response. So the filter coefficients after passing via the window, see how it looks like. This is quite smoothly truncating because the Kaiser window coefficients are varying in a very smooth fashion. So when you pass it via the Kaiser window, the impulse response of the filter using the Kaiser window, this is using Fourier series expansion method, this is using the Kaiser window. It has considerably it is considerably made smooth. So what happens to the frequency response? Now you see what is the frequency response. Now in this case we said that the corresponding transition width will have to be between 1200 and 2000. So we have achieved this, and the cutoff frequency is 1600 and the corresponding stop band attenuation is minus 40 dB. So using this Kaiser window, we could achieve all the specifications given by the user. So given the filter specifications, you will have to use all equations of the Kaiser window and then you can satisfy the requirement.